Hello everyone and welcome on today's video. My name is Wouter Peer and I'm the founder and main developer of GHEtool Cloud. From today onwards, the Turbocollector from Muovitech is implemented into GHEtool, and that's why I want to spend this time with you to discuss about how we went about the model of this probe, and also discuss about a paper that was recently written about this Turbocollector and its physical behavior. So let's jump into it. So the Turbocollector is an innovative type of heat exchanger by Muovitech, and what they did is they have a regular smooth pipe, but they installed in the extrusion process fins in it. And an important thing is that these fins, they rotate both clockwise and counterclockwise. So when you move down the pipe, you see the fins rotating in both directions. And the philosophy of this design with these fins is to induce turbulence at a lower flow rate. Now, we already talked quite a lot about turbulence in previous articles and videos, but just as a recap, turbulence says something about how easy it is for the fluid to transfer heat to the environment, to the pipe, and it's described by the Reynolds number, which is also related to fluid properties, but mostly to the flow rate. So what we have is, at a low Reynolds number, low flow rate, the fluid behaves laminar, let's just say, and all the fluid particles, they move parallel to each other. So the particles, the fluid droplets in the middle of the fluid cannot give away their heat to the pipe because they're insulated. They will never touch the pipe. So it's not that good for heat transfer. And around Reynolds number of 2300, we know that the fluid becomes more and more transient. We move towards a turbulent regime where actually the fluid droplets and the particles, they tumble across each other, and we make sure that they touch the pipe at one point or another. So the heat transfer increases, it's better, and around 4000 Reynolds number, we have a fully developed turbulent flow. Now, although the heat transfer is better in a turbulent flow, the pressure drop also increases because you need more pump energy, more pump power to really get this fluid into this turbulent flow. And the philosophy of the Turbocollector is to start this transition layer sooner, instead of starting it at 2300 for a smooth pipe, to start it in already sooner at the Reynolds number of around 1800, as we will see later. So in order to model this effect, we need something which is called computational fluid dynamics. Now, this is used all over the engineering domain. You use it in chemical plants where you have multiple pipes coming together to see the mixing. We use it to model the shape of plane wings. We use it in Formula 1 and automotive in general to model how aerodynamic a vehicle is. So it's used quite a lot, but it's really, really hard to model turbulence. Now, the reason is that all fluids, water, glycols, honey, air, it's all following the same equations, the Navier-Stokes equations, which are very famous in physics, but there is no analytical solution. It's actually one of the millennial problems of this millennium to solve them. So the only reason the only way we can solve them is by brute force numerical computational power. And it's really hard to modeling this turbulence because turbulence occurs at different time and spatial scales. So you can imagine if you look, for example, at a cloud and a plane goes through, you see this big swirling behavior at a macroscopic scale. But if you would zoom in, you see next to this big behavior, you also see smaller and smaller behaviors. So turbulence occurs at very different spatial scales and also different time scales. And in literature, there are typically three models. It's a RANS model, an LES, and a DNS model. We will not go too much into the modeling details, but I just want to show you how different models take into account turbulence. So the easiest and fastest model is the RANS model. It basically smooths out all turbulence. So you get this smoothed out version, which you can easily see on the right. There is no turbulence behavior here, but we model it by smoothing it out. So it's way faster, but you cannot model the Turbocollector with this. What is then typically used in engineering is something which is called the LES method, where we say, well, we're going to model turbulence at the macroscopic scale. So you see here some turbulent behavior, some waves, let's say. But at the small time scales and the small spatial scales, we're going to make an assumption, we're going to smooth everything out. But since the turbulence in a pipe can occur around these fins, which are very small, we really need something which is called DNS, which is the most accurate way. It's direct numerical simulation. So it takes weeks to simulate, but we are really able to simulate all the different vortices in the fluid. So you can see again both the big behavior, but now you can see sub-vortices and also where it starts. And the remaining of this presentation will be basically about this DNS, and based on the work of Niklas Hidman from the university in Gothenburg in Sweden. He did work on this in this year. And what he did is he did basically the DNS simulations for both the smooth pipe and the pipe with internal fins. Now the reason they modeled both is because we're developing a numerical model for pipes with fins, but we want to make sure that the model is accurate. So therefore we also model the smooth pipes because we know rather well how it behaves. We have correlations for that. We know the pressure drop, we know the Nusselt number. We know this. And by modeling both, we can actually make sure that the model is actually working correctly. And what they simulated was basically when does the turbulent behavior start, both at smooth and pipes with internal fins. They researched the effect of the friction factor. So thus adding fins increase the pressure drop, or the friction factor. And also the effect on the Nusselt number. We didn't talk much about the Nusselt number yet. Just briefly, the Nusselt number says something about, just as the Reynolds number, it says something about the heat transfer of the fluid. So the more turbulent the flow is, the higher the Reynolds number is, the better the heat transfer and the higher the Nusselt number. And this has an effect on the borehole tunnel resistance as well. So next to this, they also did some sensitivity analysis on the number of fins, the fin height, the twist rate, etc. We're not going to cover that in this video. It's outside the scope, but you can read the article if you're interested in it. So the results are, to jump into that, we have this type of figure. So this is for a smooth pipe. And what they did is they always started at a Reynolds number of 3,300. And then they decreased the Reynolds number until we came to a point where the turbulence stops, where the flow becomes laminar. So you can see that in 3,300 there is a light blue, let's say. The flow is fully mixed. The boundary layer does not exist. It's fully developed turbulent flow, let's say. 2,300, it's a little bit more of the boundary layer, but it's still transient, let's say. But below, in the Reynolds number of 2050, it's really, really laminar. And it's very clear because you have this thick boundary layer, this red layer, which is hotter, and in the middle you have a fluid which is colder, and it cannot give away the heat to the environment, to the pipe, due to the fact that it's insulated in this laminar flow regime. So that's for the smooth behavior. Now if you go to a turbulent pipe, we have more simulation because there is more nuance. So first of all, I want to say that all the simulations you see are for the actual Turbocollector. So they did quite a lot of simulation, but I picked the figures which are representative for the Turbocollector. So at Reynolds 3,300, we almost see no difference. We see the pipes in the background, but it's also fully developed. 2,300 as well. But then there is a difference at 250, where you see that where the smooth pipe is fully laminar, we see here the edge effects of the fins, which induces turbulence, and there is still quite some mixing here. Even if we go to lower Reynolds numbers, we see that the boundary layer increases, always a little bit, but there is still quite a lot of turbulence and transient flow, and below 1800 it's also the same as before. It's a laminar behavior. So what we see here is that the critical number of 2300, it's actually moved forward. It's now already starts at 1800. And what Niklas then did is they made also a correlation for this. And these are two very complicated figures, but I will try to explain them easily. So let's take a look at the figure on the left. This is for the friction factor. Now recall the friction factor tells you something important for the pressure drop. You typically want it to be as low as possible. So for the laminar regime, we have this analytical solution, this blue line, which decreases with increasing flow rate, with increasing Reynolds number. And after 2300, there is a jump towards the turbulent friction factor. And as you can see, the friction factor for the turbulent flow, it's almost always higher than for the laminar flow, which is what we know. We see the black dots, which were the numerical simulations for the smooth pipe. They follow this curve rather well. And then we see this diamonds here, which is actually for the turbocollector, the pipe with the alternating fins, where you see that it deviates around to 1800 because the pipe starts becoming transient. It starts to becoming turbulent, meaning that also the friction factor increases rather significantly here. On the other side, we have the thermal story. So the Nusselt number, as said, tells you something about the convective heat transfer. Now, we see here the value for the smooth pipe, and the dots are for the smooth calculation as well. Now, you can see here there are blue, red and green symbols. This has to do with the Prandtl number. Now, we're not going to cover that, but the Prandtl number is a number that varies a little bit for the fluid depending on the temperature and the type of fluid. So monopropylene glycol will have a different Prandtl number than ethylene glycol. But although this number in fluid dynamics can vary quite a lot, in geothermal engineering, it's typically between 20 and 75. So that's why there is this range here, because it has an effect on the behavior of the turbocollector. So what you can see here, the dots, they follow beautifully the Nusselt number for the smooth behavior, and then at 2300 they are becoming transient, and here they are turbulent, with the Chmielinsky correlation, which is used for the turbulent behavior. But the alternating pipes, the turbocollector, they already start this turbulence faster, and they hence also have a better heat transfer at a lower Reynolds number. So they deviate from the analytical solution or from the smooth solution here. Now, what is the effect on the borehole resistance for this? We created this figure. You can create quite a lot of figures, but this is for monoethylene glycol, 25%, for both single and double smooth and turbo pipes. Now, if we start with the green and the red one, we see here a clear laminar behavior, and both pipes behave more or less the same. There is a slight benefit of using a turbocollector here, but it's rather negligible. The most important physical aspect is the fact that the turbulence starts for the turbocollector at a lower flow rate, let's say 0.22, whereas for the smooth pipe it starts at just before 0.3 liters per second. And it's this gap where actually, since the turbocollector enhances the turbulence, that the effective borehole resistance is also smaller. And if you go towards higher flow rates, the difference again decreases, and both converge with a very, very slight benefit for the turbocollector, but it's not even visible. For the single pipe, we have the same story, but now the transition occurs sooner because we have the same flow rate, but now it's in one pipe instead of divided by two, so it occurs sooner. And you see here the same drop, which occurs first for the turbocollector and then for the smooth pipe. Now this is the story for the thermal side. We also have a pressure curve, of course. Here you see the pressure drop for both the double and the single pipes. We see that the single ones increase faster, again, because we have 100% of the flow rate through the pipe instead of only 50, because we have a W tube below. And what you can see is that the turbo collector is actually really close to the smooth pipe. It's a little bit higher, but at this scale it's not that visible. But it's here in this transition zone where you can clearly see that there is a bigger pressure drop for the turbo collector, due to the fact that, of course, it goes into a turbulent regime sooner, which is good for thermal side of things, but not so good for the pressure drop. So it increases slightly here. Now, just to end this, I wanted to pinpoint another interesting figure from the paper, which has to do with the fin height. Because you can say, well, okay, if we increase the fin height in the pipe, that would also increase the turbulence effect, right? And it does. So what you can see here is that for a fin height of 0, which is just a smooth pipe, we have a certain reference rate, Nusselt number. And for increasing fin heights, this Nusselt number increases because it induces a turbulence more and the heat transfer becomes better. But the friction factor also increases, so the pressure drop also increases. And that's why the sweet spot is actually around this 0.6 millimeters for the friction factor, because then it's more or less the same, or almost exactly the same as in smooth pipe, but the Nusselt number is already better, and it's in this range where actually the Turbocollector was designed to take into account this benefit in thermal behavior and minimize the friction losses. Now, to end this video, I just wanted to say, well, this is now implemented into GHEtool. So over in our borehole resistance step, if you go to the borehole internals, we changed the buttons to a drop-down list. So we included for you some generic U-pipes, smooth pipes, the separatus is also in there. And then we have all the turbo collectors from Muovitech with all the different pressure classes and diameters. So you can just select it and see the effect for yourself. Now, I hope you found this video interesting. If you're interested in the physics, please visit or read the article of Niklas Hidman by yourself. Share this with your colleagues, consider subscribing, and I'm looking forward to seeing you in one of our next videos. Take care.